Morning, I am Belhal. I'm going to present you two-timescale stochastic EM algorithms, a work done by Professor Ping Li at Baidu Research. The problem that we're going to tackle is a maximum likelihood estimation problem where the objective loss is a non-convex function returned as a finite sum over all observations of negated incomplete log likelihood. The incomplete likelihood is defined as the marginal of the complete likelihood noted F, and in this work, we assume that this complete likelihood belongs to the exponential family and can be summarized by sufficient statistics that only depends on the latent variable z and the observation y. A reference tool to tackle that optimization problem is the EM algorithm for expectation maximization, introduced by Dunster, Laird, and Rubin in the 70s, and composed of two steps. The first one is the expectation step, where we compute for each individual I the expectation of the statistics under the posterior distribution. And then the maximization step, using those expected values to minimize the negated complete log likelihood. When those expectations are not tractable, Wei and Tanner in the 90s introduced the Monte Carlo EM, which uses a Monte Carlo approximation of each individual expectation. But the problem of that method is that when the number of observation n is large, it does not scale. And it also requires a very huge Monte Carlo batch size in order to converge. These are the two caveats that we're going to tackle. Our method, or class of method, called Two-Timescale Stochastic, goes as follows. We first draw a single index yk, then you compute the Monte Carlo approximation for that single observation. Then you need to compute a proxy S using one of those two variants, either incremental, variance reduced, fast incremental, which will be used to update the first level of our method, where you compute STTS at a rate ρk, which is generally a constant, and the second level at a rate gamma k, which is in general in 1 over k to the power alpha. The maximization step remains unchanged. So the intuition between those two steps in our method are that the first level is used to scale to large data set. It's an incremental update and can use variance reduction when the ρk is not equal to 1. And the second level is here to temper the Monte Carlo fluctuation introduced by the Monte Carlo approximation using a Robbins-Monroe kind of update. That's why the step size is at a slower rate at 1 over k to the power alpha. We show the effectiveness of our methods on several experiments. The first one is on a synthetic data set using Gaussian mixture model, and we show the advantage of using our class of method compared to general EM or stochastic EM methods that existed before. The second one is on a real data set, which is the USPS digit data set, composed of 1,000 images per class from 0 to 9. Here we use a latent data model, which is a deformable template model, where the template is noted I and is defined as follow using a kernel matrix KP, and the deformation template is noted phi using a kernel KG. Here the goal is to learn the parameters of our kernels and of the measurement error variance. We show during the experiments that our class of method, and especially the variance reduced and the fast incremental variant, are able to retrieve the deformable template faster than the batch EM and the online and incremental variant that existed before. Thank you very much.